Okay, hopefully you were able to successfully arrange your pieces so that the sum of the square of the legs, so all of this area on the square of the legs, equaled the square on the hypotenuse. Now this is just one way. The key here is to use the four parts of the longer leg as the corners, and the square on the shorter leg goes in the middle. So there's nothing magical about the order I did that in. There are several different ways that those would arrange. So this shows that the square on the hypotenuse, which is what this is, a square on the hypotenuse, is equal to the sum of the square of the legs. And so that's what we call an area model of the theorem, but there are literally hundreds of ways to prove the Pythagorean theorem. Good thing is we're going to learn every single one of them. Okay, I'm just kidding. But here's a second proof of the Pythagorean theorem. So that one was an area model. This one uses what we just got finished learning in topic 13. So do you remember the right triangle that we had? That we had the altitude drawn from the right angle? And we determined that we had three similar right triangles as a result. Do you remember why they were similar? We have three shortcuts. We have SSS, SAS, and AA as reasons why triangles are similar. Well, we used just the angle measures themselves, and all three, the small, the medium, and the original large, had the same angle measures. One of them was 90 degrees. One we said was X, which made the other one 90 minus X. So all three of these triangles are similar to one another by the shortcut AA. And so because they are similar, we can use proportions to solve for these unknown sides. So this is question 4 in your notes. We're going to use the similar triangles as one of our ways to prove that the Pythagorean theorem is true. So the end result of that proof, of course, should be a squared plus b squared equals c squared. So notice that the legs of their large original triangle are A and B, and the hypotenuse of the original large triangle is C. Now we've introduced a new variable here, y, and so this short segment of the hypotenuse here is y, which means the other part of it has to be c minus y, since these two parts have to add up to be c. So whatever this one is, you would have to subtract from c to get this part. These two add up to get c because the y and the negative y would cancel. Okay, so we're going to begin by writing a proportion using A. Now A is a side of the smallest triangle and the largest triangle. And so in the smallest triangle, it is the side across from the right angle. So it is the hypotenuse of the small triangle. So the other side that I have an expression for of the smallest triangle is the y, which is one of the legs, and it's the shorter of the two. So I've written a ratio of hypotenuse over short leg for the smallest triangle. I'm going to do the same thing for the largest triangle, and the reason why I'm using that one is I'm still focusing on the A here. And so in the largest triangle, the hypotenuse across from the right angle is this whole side. And so we have a variable for that hypotenuse, and it's our C. And we're going to put that over the short leg of the largest triangle, which is A. So both of those ratios are hypotenuse over short leg, and we use the smallest triangle and the largest triangle. So if we cross multiply, you'll get what you're supposed to fill in on your notes. Your notes say A squared equals. Well, A times A is where that A squared comes from. What does it equal? It equals the product of these, C times Y. So that's what goes on the first blank in your notes of number 4. A squared is equal to CY. Now the next one says B squared equals. So we need a proportion with B. B is also a side of two triangles. It's a side of the medium one, and it's a side of the largest one. So this time we're going to use the medium triangle and the large triangle. in the medium triangle, B is across from the right angle, so it is the hypotenuse. Now, what other side of the medium triangle do we have an expression for? We don't have an expression for this altitude, which is its short leg, but we do for this segment, which is the long leg of the medium triangle. Remember, we said that that is C minus Y. So I'm going to set up my second ratio as hypotenuse over long leg, but I'm going to use the large triangle this time. Remember, the hypotenuse of the largest triangle is this whole length, which we call C. And the long leg of the largest triangle is the B. And so now you can see where the B squared came from. B times B, solving that proportion. Now, our other cross product here is multiplying C by C minus Y. Notice I put that in parentheses because I'm multiplying C by this whole expression. And so that's why you have two equal signs next to the B squared, because we're going to simplify this by getting rid of the parentheses by distributing the C. So B squared equals C times C minus Y, that when we distribute, C times C is C squared minus C times Y, which is CY. So that's what you have in the second blank of your notes. B squared is equal to C times C minus Y, which is equal to C squared minus CY. So hopefully you see where those came from using the concepts we just learned in topic 13. So now it tells us to sum, that means to add. We're adding these two equations together. The A squared equals CY and the B squared equals the C squared minus CY. We're adding those. And so just like you did in Algebra 1, when you were solving systems of equations by elimination, you learned you can add the two sides of an equation together. So here we get A squared plus B squared. That goes in the first two blanks on the left side of that equal sign. On the other side, we have CY plus C squared minus CY. And so in your notes it says, so what plus what equals what? Well, we have A squared plus B squared on the left side. Look what happened on the right side. This CY and this minus CY cancel each other, leaving us with C squared. So there is the Pythagorean Theorem. And that was a proof using those similar triangles from the right triangle we just finished looking at in topic 13. So that's two of the hundreds of proofs that there are on the Pythagorean Theorem, and we will definitely look at more as well. So the Pythagorean Theorem is one of the oldest theorems that we have in math, and it's named after a Greek philosopher named Pythagoras. He lived many, many years ago, of course. We're going to, in this topic, look at the Pythagorean Theorem a lot of different ways. The Pythagorean Theorem can classify triangles as being right, obtuse, or acute. We can also apply it to derive the distance formula, which we have learned and talked about. We can use it to derive the midpoint formula. There's just lots of things that we can apply the Pythagorean Theorem to. So if you look at your question 5 in your notes, we're going to start applying the Pythagorean Theorem a little bit. So it tells you that you have a right triangle and you're given the leg lengths. So we can use the Pythagorean Theorem to find the length of the hypotenuse. So in your A squared plus B squared equals C squared, the leg lengths always go in for the A and B. It doesn't matter which one is A and which one's B because you're adding them, and addition is commutative. So 5 squared plus 12 squared is the same thing as 12 squared plus 5 squared. Now it tells us the length of the hypotenuse is h, so what we would think of as C, we're really looking at as h here. So of course we want to know what 5 squared plus 12 squared is to simplify this side. Well, we know 5 squared is 25, 12 squared is 144, and 144 plus 25 is 169. So that's not the hypotenuse, that's the hypotenuse squared. So remember, to undo squaring, you take the square root. So h is the square root of 169, and since that's a perfect square, our answer is a whole number. It's 13. The next one, we're given the hypotenuse and one of the legs. and we're trying to find the length of the other leg. So now in the Pythagorean theorem, we're not putting numbers in for A and B. We're putting the hypotenuse goes in for the C, so that's the 2.5 squared. And then we're given one of the leg lengths. It really doesn't matter, again, which one you put it in for, the A or the B. Now, it told me the other leg was X. I wrote it as B, but it can be X. That's fine. So that's the equation we're solving. 2 squared plus X squared equals 2.5 squared. Well, we know that 2 squared is 4, and we can find 2.5 squared, which is just 6.25. And so we can get x squared by itself by subtracting the 4 from both sides. So we have x squared equals 2.25, and we know we have to undo that squaring with a square root. And you may think that that looks like a horrible problem, but that's really a perfect square. If you find the square root of the square root of 2.25 in your calculator, you'll see that you get a decimal, but it at least terminates. There's no rounding that's necessary. And so that is 1.5. Now, just to get you to know that it doesn't always have to be A, B's, and C's, it says a right triangle has hypotenuse of length D. The legs are U and G. So how would we write that using the Pythagorean theorem? So remember, the hypotenuse goes in for the C. The legs go in for the A and B. So we would write that as U squared plus G squared equals D squared. Or remember, the legs can be in any order. You could write that as G squared plus U squared equals D squared. But the hypotenuse has to be squared on one side of the equation by itself. That's the important thing. On question 6, you can use the Pythagorean theorem to determine whether a triangle is a right triangle or not. If it is right, it will satisfy the Pythagorean theorem. So you'll be able to put the 3 numbers in for the A, B, and C, and if it makes a true statement, then it is a right triangle. Now, the important thing is to know which one of these goes in for C. A and B, it doesn't matter the order, but you have to find the longest length, and that's what has to go in for the C. The 8 and 15 can go in for the A and B in any order. So this is what we're trying to check. Is that true or not? Well, you can put in your calculator 8 squared plus 15 squared, which is 64, plus 225, which is 289. And then you can look at what 17 squared is, which is also 289. So since it worked in the equation, then we know, yes, that that is a right triangle for sure. Anytime the 3 sides of a right triangle are all whole numbers, we call that a Pythagorean triple. So we just learned that the 8, 15, 17 is a Pythagorean triple. And we've talked about that several times this year already. The most famous and smallest Pythagorean triple is the 3, 4, 5 triangle. So again, that's when they're all whole number values. So I want you to go ahead and complete question 8 in your notes. You're given 6 triangle lengths, and you're supposed to determine whether they make up a right triangle or not a right triangle. So again, you're just putting those numbers into the Pythagorean theorem to see if it works and satisfies the equation. If it does, it makes it a right triangle. If it does not, it is not a right triangle. We're not saying that they all have to be whole numbers, so don't think that just because this is a radical that this cannot be a right triangle. As long as you can put these into the Pythagorean theorem and it's true, then it is a right triangle. Remember that you have to put the longest or the largest number in for the C value. So I'm going to stop this video here. When you get those question 8 done, you can start the third and final video.